Explorations. Probing global diversification. We travel the world so you don't have to.
Where on Earth or in space did these stars come from? What magic created these little diamonds in the night sky? Starlight, star bright, starlight. In this show, a physics professor will talk about how stars are formed and the important role they play in the formation of a galaxy. Also, an astronomer will discuss how the constellations were important navigation tools in ancient times. He will also talk about the difference between astrology and astronomy. And we will hear from a star sound specialist about how each star carries its own unique sound and how they may affect us. What are the elements that contribute to the formation of a star? Listen to Christine Wilson, physics professor at McMaster University, talk about how stars are formed, and the pulses they emit is what astronomers will study to follow the life cycle of a star. Learn about pulsars and how they can play an important role in the formation of a galaxy. She will discuss the science behind the star and how we are able to get the sound of a star.
I mean, this is kind of perhaps a far-reaching question, or maybe it's not. Maybe it's quite simple. How are stars formed?
Well, we think we understand the basic outlines of how a star like our sun forms. It starts off with a region of space that contains a lot of gas, and that region of space needs to have enough of a concentration of matter that it becomes unstable under its own gravity, so that the force of gravity trying to pull the matter in towards the center gets larger than the pressure and other things that are trying to hold it up and keep it from collapsing. So when you get enough matter in a small volume, it will start to collapse, and ultimately that collapse will lead to a star like our sun if there's enough mass present. Along the way, what happens, though, is the cloud of gas often has some rotation associated with it. And so as it collapses, it starts to spin faster and faster. And this spinning causes the collapse to not proceed in a sort of fully spherical fashion, but the matter collapses down to form a disk, a flattened structure. You can kind of think of this like a dinner plate that's rotating. And then matter keeps funneling into the center through the disk. And the formation of that disk is actually really important for two things. One of the things is that it generates large outflows of material out the centers of the disk that act to carry away some of the material, and also this angular momentum, the rotational energy as well, gets carried away. But also those disks are where planets form. And so as the material comes into the center, it gets denser and denser and hotter, and eventually gets hot enough that nuclear fusion starts. And at that point, you've formed a star. And you may be going on to continue to form planets in the disk, but eventually the energy from the star and the fact that it runs out of material at the large scales will cause the star to stop accreting matter, and it will blow away the gas in the disk. And if you're lucky, you're left with a star with a system of planets around it.
Is there a particular time when the star is being formed when the energy is more concentrated?
No, I don't really think so. So the energy as the star is being formed comes out in different ways. So in the early phases when a star is being formed, when it isn't burning, doing nuclear fusion in its center yet, the gas, the material that's forming the star is getting quite dense and warm, but it's still nowhere near as warm as our sun. And so as a result, that what we call a protostar, because it's going to be a star, but it isn't yet, that protostar emits its radiation not as visible light, but at longer wavelengths into the infrared. So it's more like it's producing heat energy like a fire would than visible light. Now, fire is not a great analogy because it also produces light, obviously. But so these stars, when they're protostars, you actually can't see them, or often can't see them, with optical light telescopes. You have to use infrared or radio telescopes to find them. As they evolve, they go through a phase as they're sort of settling down. When they're very young, they can be very active. They can have lots of star spots on their surface, kind of like the sunspots, but often bigger. And along with those star spots, there can be flares. And so those young, sort of unsettled teenage stars can be putting off ultraviolet radiation and X-ray radiation, primarily in these flares. And this is actually one of the things that affects and destroys the disk around the young star, is the energy from this X-ray radiation, in particular from the flares.
What about the lifespan of a star? Do they usually last for at least a specific time?
Okay, so a star like our sun will burn hydrogen in its center for about 10 billion years. And once it's done burning hydrogen in its center, it starts to burn hydrogen in a shell around its core, but it goes through a lot of structural changes that causes it to get bigger and cooler and then brighter. And eventually it goes through some pulsations, sheds its outer envelope, becomes a white dwarf star, and cools away into oblivion. And all those phases after it finishes burning its fuel in its center add about 10% to the lifetime of the star only. So astronomers tend to think about the period of time that the star burns hydrogen in its center as being the life of the star. So for our sun, that's about 10 billion years. For more massive stars, so a star that's, say, 30 times the mass of our sun, it burns at much higher temperatures. It has more fuel to burn, but it uses it up so much more quickly that its lifetime is only about 30 million years. And then there are stars less massive than our sun, say 30% the mass of our sun, where their lifetime is longer than the age of the universe. So every one of those stars ever formed is still around today. So the lifetime is known and can be measured and modeled quite well using models of the internal structure of stars, but it depends on the mass of the star.
Nina was discussing the whole idea of stars emitting sounds, and that these sounds can be listened to or measured. Talk a little bit about that, please.
Well, so the idea of a star emitting a sound, I think, is a little bit complicated. So, first of all, a sound wave, like we have on Earth, needs a medium to travel through. So there can be sound waves inside a star, but those sound waves can't get to us as a sound wave because between the star and us, there's a vacuum. There's no medium to carry the sound wave. Okay, so if people think about sound waves from a star, there are a couple of different things that occur to me when you say that. The first is that a star like our sun has some large-scale, low-level oscillations going on inside it. It's kind of, it's almost like it's ringing inside, pulsating back and forth. And it's been a while since I've read about this, but I feel like the main period of those oscillations is about 5 minutes. So if you translated that into a sound wave, it would be very, very, very low frequency, I mean too low for us to hear. A typical sound that we hear on Earth is oscillates about 400 times per second. So that's 1 over 400 seconds is its period. The other type of sound that people might be referring to is pulsars. So pulsars are the dead remains of some massive stars. They're extremely high density. They have very strong magnetic fields, and they spin very fast. And so as a part of this very rapid spinning and high magnetic field, these pulsars produce radio waves, and the radio waves are modulated. They come as a pulse everywhere from about every 1 or a few tens of seconds down to maybe a millisecond. And so you could convert that frequency of how often that pulse arrives into an equivalent sound that we could hear. But the neutron star itself isn't really producing the sound. We're just taking the frequency of its pulse and converting it into an equivalent sound wave. So when people have heard the sound produced by a star, it may be one of these pulsar signals converted into sound.
Explorations. Probing global diversification. We travel the world so you don't have to.
Where on Earth or in space did these stars come from? What magic created these little diamonds in the night sky? Starlight, star bright, starlight.
Explorations. Probing global diversification. We travel the world so you don't have to.